All right. An experiment is conducted to compare the maximum load capacity in tons. Maximum load capacity, this is the maximum weight that can be tolerated without breaking, for two different alloys, A and B. It is known that the standard deviations in load capacity are equal at 4 tons each. The experiment is conducted on 60 specimens of each alloy, and the results are that the mean load capacity for A was 36.9, and the sample mean for B was 34.9. So that would mean the difference there, x bar minus sub A minus x bar sub B is equal to 2, right? 36.9 minus 34.9, that's equal to 2. So the manufacturers of alloy A are convinced that this evidence shows conclusively that the mean load capacity, that the mean load capacity, the mean maximum, I guess I gotta be careful, right? Because we're talking about the maximum load capacity, but this is the mean of that. So this is the mean maximum load capacity. In other words, their alloy on average is stronger than alloy B on average. And they think that this evidence strongly supports that claim. Now, manufacturer of alloy B says, we only ran the experiment once, and this could, if easily, I missed a Y here, easily have given a difference of 2. We only ran the experiment of once. This is not that weird of a value to have for a difference there, even if the two population means are equal. So we are going to make an argument that the manufacturers of alloy B are wrong by computing a probability here. Okay, and this is a little bit of foreshadowing into some future tools and techniques. But without using any of those terms, let's just answer with what we know here, okay? So what is this probability asking us to do? This probability is saying, find the probability that x bar A minus x bar B is greater than 2, given that these are the same, okay? So this conditional statement right here is saying, let's assume that alloy B people are correct, all right? For argument's sake, let's just assume they're right and say, you know what? Let's assume that these means are equal. What is the probability then of getting this difference? What's the probability of getting a difference of 2 or something more extreme than 2, given that they are quote unquote equal, supposedly equal, given that they are equal? All right. Well, we can do this. Let's see what we have here. Remember that in general, we would say the difference of x1 bar minus x2 bar follows a normal distribution with a mean mu1 minus mu2 and a variance of sigma 1 squared over n1 plus sigma 2 squared over n2. All right. So in this case, if we assume that these are equal, then mu sub A minus mu sub B is equal to 0. So x1, let's say this is xa bar minus xb bar, follows a normal distribution with a mean of 0. And what would the variance parameter be here? We need sigma 1 squared, and we need n1. Sigma 1 squared over n1. And we need sigma 2 squared over n2. Sigma 1 squared. Well, it is known the two standard deviations are equal at 4 tons each. So it is known that sigma 1 is 4 and sigma 2 is 4. So this is 4 squared, or 16. And then what is the population size for n1? We have 60 specimens on each alloy. So this is 16 over 60 plus 16 over 60, because those are the same parameters for each. And so this is going to be equal to, so 16 plus 16, that's 32 over 60 is the variance there. 32 over 60 is the variance. And 32 over 60 is the variance. I'm just getting ready here because I know I'm going to need the standard deviation. The standard deviation of 32 over 60 is approximately equal to 0.73. Okay, just because I know I'm going to need that when I do my probability computation, because for conversion, we use the standard deviation, not just the variance. So what do we have so far? X bar A minus X bar B follows a normal distribution here, right? And we wouldn't know what this is. We wouldn't know what this is unless we've assumed that this is true. And that's all this conditional statement is saying at this point, right? Is given that those are true, now compute this probability. All right. Well, let's go ahead and do that. What is then the probability that XA bar minus XB bar is greater than 2? Given that these are true, it's going to follow this distribution here. And so let's see, this is going to be equal to the probability. We can convert this to a standard normal random variable. 2 minus the mean of 0 divided by the standard deviation, which we know to be 0.73. So let's go ahead and plug that in there. Approximately 0.73. So the desired probability then is probably that z is greater than, what is 2 divided by 0.73 here? That is 2.7397. So that's about 2, very, very close to 2.74. Very close to 2.74. All right, we can use the standard normal table here, but we have to look at the complement because that's greater than, so we want to convert this to a less than problem. Less than 0.274. And let's go ahead and look at our table. Where's 2.74 in our standard normal table here? 2.7, 0, 1, 2, 3, 4 is 0.9969. So 1 minus 0.9969. 0.0031. This is 0.0031 after we did the subtraction. Okay, after we did the subtraction. So, what do we conclude here? What do we conclude here? What is our argument? Because remember the goal, make an argument that the manufacturers of alloy B are wrong. All right, so what did we have here? Basically what we can try to say, let's see if we can't summarize this in words carefully, right? So, assuming that mu of A is equal to mu sub B, that the average alloy have a equal maximum load capacity, assuming those are equal, the probability of getting two samples, the probability of getting a sample difference, mu sub A bar minus mu sub B bar, a sample difference. Actually, well, we've used the letters X, right, for the sample. This is our sample, not our parameter. X sub A bar, getting a sample difference bigger than 2. Getting a sample difference bigger than 2. Notice this could be including 2, right? Because we're talking about continuous things here. But we specifically bigger than 2 is less than, look at this, 0.0031. This is less than 1%. This is less than 1%. This is less than 1%. So our support then is very strong in terms of alloy A, in the sense that it is very unlikely to get a difference of 2 or larger, which is what we observed. Therefore, it is very unlikely to observe that our sample difference, right? It's very unlikely to observe that our sample difference is equal to 2. And so one would conclude, we can therefore sort of conclude that mu sub A is not only not equal to it, right? But we include that it's better than mu sub B. That would be our conclusion. That would be our conclusion, right? Because this probability that you get a value of 2 or larger, more extreme than 2, is very negligible. There's a less than 1% chance that we're going to, if we ran this again, we only did this, if we ran this again, there is almost it is almost impossible, less than 1% chance that we would get a value. Think about the complement of being larger than 2. That would be smaller than 2. Smaller than 2. If we ran this again 99 times out of 100, we're going to get a difference that's smaller than 2. And so the fact that this happened, even though we only ran it once, this is good evidence that supports that alloy A has an average maximum load capacity that is stronger than alloy B.